Nature of scientific knowledge. There are many different investigation methods, but here is a representative one. 1. Make an observation that is objective and may be duplicated by other scientists. Next, gather and evaluate available information about the observation. Make an educated guess or hypothesis to explain the cause of the observation. It must be testable. Conduct an experiment to test the hypothesis. Analyze the data and report if the hypothesis was or was not supported. Share the data with other researchers. The results also need to be communicated to the general public so funding and resource decisions can be made by governments. And finally, make new predictions based on the data analysis. Some definitions. Observations, experiments, research, and discussions can lead to new scientific questions, hypotheses, and theories. A question provides a clear path for research. It arises from curiosity about a natural phenomenon. A hypothesis is a statement that proposes a testable answer to the question. Observations or observational studies take measurements or surveys of a sample without trying to affect them. In controlled experiments, scientists carry out tests, trials, or procedures by manipulating variables to see the effect of each change. Scientific progress can be made from observations and controlled experiments. Observations made by Tycho Brahe, and we talked about him earlier, enabled Johannes Kepler to create his laws concerning the motion of the moon and the planets as discussed in the first topic of this unit. Marie Curie carried out experiments to explain the radiation coming from certain elements. During this work, she discovered two new elements, polonium and radium, and stated that the radiation was coming from the nucleus. They were not X-rays, but gamma rays. In experiments, scientists carry out tests, trials, or procedures by manipulating the variables to see the effect of each change. Now, we said that on the previous slides, but that has to be emphasized. The words theory and law have specific meanings in science. Both follow observations, questions, and experiments. A theory explains why many types of physical phenomena occur and has been repeatedly tested by many researchers and found to be valid and true. A law describes physical phenomena and cause and effect relationships. It makes no claim as to why the phenomena behave as they do. Like a theory, it has been repeatedly tested and found to be valid. Scientific knowledge is based on questions that can be answered by experiment, detailed observations, or calculations. The knowledge should lead to models, such as theories and laws, that are used to make predictions about related phenomena not yet observed. If the predictions fail, then the models must be modified to fit the new results. The best models unify different, previously separate observations, like how the electromagnetic theory combined electricity and magnetism principles. Scientific knowledge is always subject to change as more complete experiments or observations are made. Just as Einstein's special theory of relativity for objects moving near the speed of light extended Newton's three laws for motion, didn't get rid of them, just built upon them. Having models for one type of phenomena are also used to create new hypotheses and questions without having to start all over. For example, Michael Faraday and James Clerk Maxwell created the field theory model to explain electromagnetism in the 19th century. In the 20th century, physicists built on the field theory model to help create quantum physics. Max Planck, while researching blackbody radiation, modeled the phenomenon as light being composed of small packets of energy. Again, this laid the ground for quantum physics and also helped Albert Einstein explain the photoelectric effect. In addition to explaining phenomena with theories and laws, a different type of model is used to make natural phenomena more understandable. For example, electric potential, otherwise known as voltage, and its relationship to electric fields uses similar concepts to topographic maps. Lines on maps are drawn to represent heights above seawater. The closer the lines are to each other indicates steeper changes in elevation. The closer the lines are to each other on a plot of electric potential indicates stronger electric fields. Electric current is modeled as a flow of water, since electrons are quote, flowing through the wires. A limitation of this model is that water flow does not need an unbroken or complete path to flow, where electrons need both. For both of these examples, people are more familiar with maps and water than electric potential and current.